What if we got our energy from space? Our world needs clean energy. It's no longer a preference, but a necessity to keep up with the demands of the world's economies. Fossil fuels can only become more expensive, while their rising burden to global health and stability is becoming unacceptable. However, renewable energy from the sun and wind doesn't work all the time. But if we got it from space, it promises to be limitless, uninterrupted, pollution-free, and immune to accidents. The technology features in nearly every space science odyssey story, but with the promise of cheaper, heavy-lift rockets on the horizon and empowered by modern manufacturing technologies, humanity may not be too far away from harnessing the uninterrupted power of the sun from space in the not-too-distant future. Picture an immense rectangle of glass floating in space, 10 kilometers long and 5 kilometers wide, sparkling blue with vast arrays of silicon solar panels. Its skeleton is a vast network of triangular trusses, each the size of an apartment building, welded end to end. This is the original concept for a solar power satellite. It hangs over one spot on Earth permanently, like a fixed star in the sky, thanks to its geostationary orbit. It will face the sun for 30 years while shrugging off all forms of damage with its bulk. 12% of the sunlight that reaches it will be converted into electricity, totaling 8.5 gigawatts. That's as much as 20 natural gas power plants or 8 nuclear reactors. All that electricity is directed into radio frequency generator modules, the same type used in cell towers, but arranged into a grid 1 kilometer wide. Together, they form an antenna that can direct a microwave beam down to the Earth 35,800 kilometers below. That beam is how the satellite powers our planet. It is met on our end by a receiver called a rectifying antenna, and because the beam spreads over its journey to Earth, the receiver has to be 10 kilometers in diameter. A rectifying antenna is merely a grid of wires connected to simple diodes, the same technology used to get a signal from contactless cards or RFID tags today, but scaled up. Such a receiver could be built anywhere, as it does not block sunlight, works in the rain, and the energy it receives is spread out over such a large area that it could never hurt anyone. 5 gigawatts remain after converting the microwaves back into electricity. One solar power station of this design can power 5 cities the size of Boston. It delivers this power night and day, just like nuclear reactors, hydroelectric dams, or coal plants do, while also avoiding the risk of meltdowns, floodings, or toxic leaks. But to achieve this requires a mighty effort. The solar power station weighs 50,000 tons when completed. It's more than the Titanic and has to be built in orbit. The original concept called for an army of astronauts to work out of a stadium-sized hangar for months on end, connecting panels and welding together trusses in a vacuum. The parts they needed would have had to be launched from the ground into low Earth orbit, then raised to geostationary orbit by a specialized transfer vehicle. Even after it was completed, workers would cycle in to perform maintenance, while 93 tons of fuel would be delivered each year to resupply the small thrusters, maintaining its position. This dream of a solar-powered behemoth is nearly 60 years old. For most of that time, the thought of building it was beyond insane, pushing the concept back into science fiction. So why are engineers clinging on to this idea? Well, it's simple. The surface of the sun is a 5,800 Kelvin furnace 150 million kilometers away. An intensity of 64 million watts per square meter is enough to turn most materials into hot vapors. But sunlight spreads out on its way to Earth until it falls to 1,386 watts per square meter. We don't get that much on the surface though. Gases like carbon dioxide and water vapor in our atmosphere absorb a portion of that light and scatter the rest, reducing it to a maximum of 1,100 watts per square meter. Our Earth is not perfectly positioned to catch this sunlight either. Its inclination means that only a tiny patch of ground actually receives the maximum intensity of sunlight, and only during midday, and only in clear weather. A patch of land in California receives an average of 250 watts per square meter across the year, while the same patch in Dublin averages less than 110 watts. That's what regular solar panels have to work with. Commercially available technology converts 20% of the incident light into electricity, so the average output of 1 square meter is 20 to 50 watts. But electricity demand doesn't usually care whether the sun is shining or not, so additional panels are needed to keep up with demand when the sun is low, and even more to fill the batteries to last the night. In geostationary orbit, a solar panel receives the full intensity of sunlight, without interruption or variation. Technically, a satellite up there passes through the Earth's shadow for a few minutes each year, but that can be ignored. The same solar panel in space is 5 to 12 times more productive than on the ground, and because it doesn't need to fill up batteries for the night, ends up being worth 10 to 24 times as much. Even after losses from converting their output into microwaves and back into electricity are factored in, it is a massive advantage. Space-based solar power is all about harnessing that huge performance multiplier to make sending those panels up into orbit worthwhile. The trouble is that a 50,000-ton structure built in space is just a step too far. How did anyone believe this was a realistic plan? Well, it was a desperate idea born from a time of crisis. In the 1970s, the world was struck by 2 oil shocks. Reduced oil exports from the Middle East caused the price per barrel to skyrocket, with the United States feeling it the hardest. In the inflated adjusted dollars, the price per barrel rose from below $30 to $69 in 1973, then again to $156 in 1979. Industries halted and muscle cars went extinct. Politicians and engineers in the West believed their world was going to be forever beholden to the whims of oil-exporting countries, motivating them to break the hold that fossil fuels had on their economies. The result was that a plethora of new oil-free energy technologies were taken seriously for the first time and got public funding for their development. Fracking for domestic natural gas, hydrogen fuels for transportation, and alternative energy sources from sun and wind were investigated. Space-based solar power was one of these ideas that received attention. At the center of their efforts was the hope of combining 2 new developments: an upcoming space industry and the plans for a fully reusable space shuttle. The space shuttle was supposed to be a simple workhorse that would provide rapid, cheap access to space, so anyone could try their luck in the new frontier. Many versions and updates were created, with our 10-kilometer wide design being one of them. But in the end, it was a failure. But the space industry didn't take off as many had hoped. After Apollo, NASA cancelled its Mars missions, scaled down its space stations, and never returned to the moon. The space shuttle was an even bigger disappointment. Instead of a straightforward orbital truck, it became a partially reusable half-military spacecraft that flew less than 5 times a year and delivered payloads of $54,500 per kilogram. Only half of that payload would reach geostationary orbit after being moved by a transfer vehicle, so the actual cost to launch a solar power station would be multiplied by 2. The full 50,000-ton design would have cost over $5 trillion in launches alone. But what really killed the solar power station concept was the return of oil. Most efforts into finding alternative forms of energy were abandoned when the oil shortage turned into an oil glut in 1980. The price of a barrel of crude fell to $34 and all was well again. The birds sang, the fish did whatever fish do, and the world lived happily ever after. But today, the US is facing a rising rival power in the East. It's worried about foreign nations cutting off the supply of raw materials, trying to maintain its lead in space and regain its energy independence. There is a global crisis that's pushing engineers to come up with new ways to produce energy while cutting out fossil fuels. Fracking activity is higher than ever. Hydrogen-fueled transportation is being attempted, and renewable energy sources are growing at record rates. Meanwhile, SpaceX, Rocket Lab, and other private space companies are coming up with reusable launch vehicles that promise rapid, cheap access to space while sharing visions of a space industry reaching Mars. Okay, so maybe the world isn't so different from before. Does this mean it's time for space-based solar power to shine again? Well, no. At least, not while it resembles anything like the original concept. The cost of space launch is less than $3,000 per kilogram thanks to SpaceX's Falcon 9, and could fall further as more heavy-lift vehicles enter the market. We also have much better solar arrays, like the Rosas recently installed on the International Space Station, that exceed 30% efficiency. Rather than silicon on stiff glass panels, the new arrays use multiple layers of semiconductors to capture a much greater portion of the solar spectrum while resting on thin plastic sheets. Yet, even with these improvements, a 70s-style power satellite would cost over $400 billion. The army of astronauts needed to assemble it are nowhere to be seen either. That's without even looking at the hassle of laying down about 100 million square meters of wire mesh on the ground to receive the microwaves. A modern redesign is needed. There are many options, from government-funded projects in the UK, China, and Japan to privately developed designs. The Cassiopeia is one of these new-generation solar power stations. It's 4 kilometers long and 1.7 kilometers wide. At each end is a twisted pair of mirrors that capture sunlight and concentrates it onto exceptionally high-performance solar panels, weighing just 240 grams per square meter, yet able to convert 39% of the light reaching them into electricity. Sandwiched with the panels are microwave antennas in a helical shape that is always able to point a beam at the Earth without having to move. The whole structure is made from modules that just snap together instead of having to be welded. Without any moving parts and easily assembled by robots, it eliminates any reliance on human workers up in space. What's more, the modules can be moved into geostationary orbit using electric thrusters, a propulsion technology we regularly use today that's 10 times more efficient than any chemical rocket. The completed Cassiopeia would weigh 1,348 tons for an output of 1 gigawatt. At that same weight, the 70s-era power satellite would output 10 times less. These features would reduce the cost of launching a solar power satellite to $4 or $5 billion. Sadly, this is still too much. Economists would have many arguments. The whole project is estimated to cost $20 billion and take a decade to complete. They would compare the 1 gigawatt generated to a less costly nuclear power station, or just another field of solar panels on the ground. It's dreary, but the reality is, a concept needs to be radically better than existing solutions to attract the money needed to make it real. Radical concepts, however, are not in short supply. Space-based solar power has received numerous innovative designs over the years, using technologies that are not quite ready yet, or unconventional approaches, but these quirks might be just what the concept needs. For example, instead of thinking of a power satellite as a uniform entity, imagine it as a swarm of satellites merely occupying the same orbit. The individual elements are the same mass as existing geostationary satellites, equipped with their own solar panels and electric thrusters to move themselves into position. Their most unique feature is switching out a microwave beam for an infrared laser, allowing each swarm unit to export its power over 35,800 kilometers using a centimeter-scale mirror, rather than requiring a kilometer-scale antenna. The receiver on the ground would have to be a specialized solar panel tuned to the laser's wavelength, converting 60 to 80% of the laser's beam back into electricity. We'd want to reduce the size of the receiver to a few hundred meters by increasing the intensity of the lasers, perhaps to 1000 watts per square meter, or equal to midday sunlight. The upside of this approach is that the swarm can start delivering power as soon as the first unit reaches geostationary orbit and can be gradually expanded from there. If SpaceX makes good on its Starship promises and offers launch prices of under $200 per kilogram, then these swarm satellites would cost roughly $1 million each, and getting a 1 gigawatt swarm would cost $1 billion. That's a price tag competitive with any natural gas power plant or solar farm today. The range and focus of the lasers also allows them to target other satellites in lower orbits, keeping them powered up even when they pass into Earth's shadow. Space-to-space transmission can command a much better price than space-to-ground after all, as there's much less competition there. The same goes for military bases who can't deploy kilometre-wide antennas to receive microwaves, but would still like a source of energy that eliminates reliance on vulnerable fuel truck convoys. The downside is that infrared lasers need to aim around or channel through heavy cloud cover to reach customers on the ground. And also the small matter of people being afraid of space lasers, however weak or diffuse they are. Reflect Orbital is developing a completely different approach that skips the step of converting electricity into a beam and then back into electricity. Large flat mirrors could reflect sunlight down to the surface in a move that solves a number of this technology's problems. The receiver is simply a regular solar panel that's already on the ground, working normally during the day, but at night it continues producing electricity using reflected sunlight. But I'll be honest, this script originally just made fun of Reflect Orbital. Sunlight is cheap, launching satellites is expensive, and the light pollution it would cause would be insane. How could this ever work? I had this joke in there that involved the meme of William Dafoe staring up at the sky and having his eyes burned out. But then a good friend of mine, Charlie Garcia, joined their company as chief engineer. And that guy is one of the smartest people I know, and I knew he would agree to answering some of the hardest questions facing their company's future, so let's do that instead of resorting to adding more negativity to the internet. And I will apologize now for the insane noise in the Reflect Orbital office. You will be hearing the hellscape of LA a lot in the background. But before we get to the interview, I want to talk about how I usually research these videos. Sometimes I do it like this, where I interview the people working on the problem that I'm talking about. Other times I use college textbooks or scientific papers or even declassified documents, but I rarely use other tech journalists' work. IEEE Spectrum is a magazine released by the Institute of Electrical and Electronic Engineers, and I have been a subscriber for a long time, so I was really happy when they reached out to sponsor the channel. In a world full of hype and bubbles, Spectrum is one of the few voices I trust to deliver clear technical science journalism. This helps me stay on top of emerging technologies for this channel, but it has also helped me immensely with how I have invested my savings. Everyone loves investing in high-growth tech stocks, and being ahead of the curve on where legitimate breakthroughs are happening can give you a small advantage. And it's truly great writing. Just look at this article about a potential laser-propelled interstellar swarm to Proxima b, a topic I am currently researching for a future Real Engineering video. It's beautifully illustrated, there aren't any annoying ads interrupting your reading, and it's honestly just beautiful to look at. On the very next page is another beautifully illustrated article about engineers working to sequence the DNA of all life on Earth for the Earth Biogenome Project, something I had never heard about before. This isn't the layman magazine you see on a store shelf. When you subscribe, you're joining a global community of some of the most accomplished engineers on the planet. They of course have a digital-only subscription, but there is so much to be said for having a physical magazine in your hands. It's tactile, it's collectible, but most importantly for me, it's free from the constant notifications and distractions of working online. Getting a coffee in the morning and slowly ramping into my day away from the screens and distractions with a magazine or book is my favorite way to get my brain kickstarted for a day of research and writing. And with the holidays coming up, it's a great gift idea for the nerdy engineer in your life, and maybe that just means gifting it to yourself. IEEE are offering 20% off their usual subscription fee, which you can get by visiting spectrum.ieee.org/real-engineering or by scanning the QR code on screen now. And with that, let's get back to our interview with Charlie Garcia. You're planning to launch into low Earth orbit, right? But that will mean the ground track of the satellite will be shifting under it every time it goes around the planet. So the satellite will only be visible to individual targets for a very brief period of time, and obviously electricity is really cheap. So how can they recover their costs in low Earth orbit?
This is like sort of fundamental to the company. This is actually this is the best question because it touches economics, orbital dynamics, it touches satellite constellation design, it touches sales and business development. It's kind of the core thesis of the company is that the utilization of these satellites can be high enough that this is a valuable business. And so to talk about why what I just showed you is important is the first satellites that we launch aren't going on an orbit like the International Space Station is where it spends a significant portion of its time in eclipse, unable to serve customers. And it's also not spending its time flying over places that don't have value for the light. Because electricity is most valuable at, around sunrise and around sunset when people are waking up, they're doing their morning routines, industries are getting started, or when they're getting home, they're watching television, they're wrapping up their day, because renewable sources tend to be at their lowest generating potential then, while the power demand is highest at those times. So you're really relying on these peaker plants. And so by choosing this terminator chasing orbit, where you're orbiting over, kind of the day-night transition, you're selling sunlight to solar panels when it's most valuable. The satellites themselves are always in sunlight, and so you can continuously be serving customers that are below you. And then you're always over the customers that have the most immediate need for your service. And also, there's fewer impacts, right at twilight, because there's already some light there. So you're having a less significant impact on wildlife that may have sensitive daylight cycle activity. And also, people, light pollution is a real and growing concern. And so that's a really great place to start this service. And then also, the entire Earth will rotate underneath of you. So you can serve the entire globe with just this one constellation. So it's really a global investment in infrastructure, helping deploy clean energy across the world with just this one constellation, sort of similar to like Starlink, right? Starlink provides internet whether you're in rural America or in rural Asia, which is a really powerful, unifying aspect of space. So as far as downtime goes, obviously you can only serve when you're over a customer, and that we expect that to happen somewhere between 7 and 30% of the time, depending on the season and the orbit. So we actually don't expect our satellites to be highly utilized. But that comes back to us in the design of the satellite. So because we know that the satellite won't be serving customers continuously, we actually designed the satellite to be a little smaller on the solar array and the reaction wheels and some other components than it might otherwise be, so that we spend time in between customers recharging.
So, the recharging aspect is actually really important. Their satellite's orientation will be controlled by reaction wheels, but the size of reaction wheels needed is determined by the satellite's moment of inertia. How much it resists changes to its rotation. And moment of inertia is determined by the satellite mass and its distance from the rotational axis. And these mirrors are going to be big, so those reaction wheels are going to be a huge portion of the satellite's mass, increasing launch costs. But they also need time to desaturate those reaction wheels. This is part of the recharging process, so I asked Charlie about that. You will also have to desaturate those reaction wheels too, right? Will that not be really difficult with how big they are?
Okay, this is super cool. We actually just figured this out, so I'm so excited to talk about it. So the satellite has these reaction wheels that steer the spacecraft, and that allows us to track a target on the ground. As you do that, you pick up spurious disturbances, right? You get bumped a little by some solar pressure, a couple atoms of oxygen hit you, the gravity gradient stabilization effect of the Earth tugs on one part of your satellite a little differently. And so when you bring the satellite to a stop after serving a customer, your reaction wheel hasn't gone back to the speed it started at. It might have picked up a little velocity in one way or the other. And over time, this effect is significant. And so eventually your reaction wheel would reach its maximum speed, and you wouldn't be able to steer the satellite anymore. You'd saturate. We call it saturating the reaction wheel. So we need to dump momentum back to the Earth. Well, how can you do that? You don't have anything to push on. That's not quite true. The Earth has a very large, fairly weak, but very large magnetic field. And so as the satellite's moving through the magnetic field, we actually turn on and off like bars, like copper wire wrapped around iron rods. We call them magnetorquers. And we literally push infinitesimally against the Earth's magnetic field. And that steers us a little bit. But that's not actually quite enough force, because our sail is so large, you get such a large turning moment from aerodynamics, that actually part of the way we steer the mirror is also aerodynamically, where the tiny amounts of drag we get, we actually flip the mirror between two orientations, almost like a sailboat tacking against the wind, to dump momentum from the reaction wheels back to the minuscule number of atoms that are hitting the spacecraft as we fly past them. And this is important because in order to solar sail, in order to use the sun's radiation pressure to control the orbit of our spacecraft, we need to hold very specific angles for long periods of time. And so if we saturate our reaction wheels, the satellite will tumble and we'll lose the ability to steer our orbit, and it will eventually deorbit relatively quickly.
Can you actually use control surfaces for a solar sail?
You totally can. It's so cool. You can put they're literally called empennages, where you put these asymmetric devices at the end of the solar sail to make it passively stable in one direction. So if you lose control of the satellite, it adopts a low drag mode. Unfortunately, Reflect Orbital has some challenges with doing that because they're at the edge of the mirror, so they contribute disproportionately to the mass moment of inertia of the satellite, and that means your reaction wheels have to get even bigger. So at a constellation scale, right, we're trying to design these satellites to be very, very cost effective, very, very cheap. We would prefer to not have to do that, but that's absolutely a kind of technology we've looked into that's been studied not just by us, but by other solar sailors as well. But yeah, that's absolutely a way to do it.
That's class. So I guess the other factor to the financial feasibility of this would be how long the satellite's life cycle is. How long can you actually expect the satellite to stay up in orbit?
Yeah, that's a great question. We've got a demo mission going up next year, and we'll be really quite happy if that lasts a year. There's some really interesting material science where actually the oxygen in the space environment can be atomic oxygen. It's not paired with another oxygen atom. And in that case, it can react very aggressively with the polymer that makes up our mirror. Actually, at the risk of doing show and tell, I've got a piece of it right here. You can see just the heat from my hand is enough that it will float.
What is it?
This is 2.5 micron vapor deposited aluminum coated polymer. The exact polymer is proprietary, unfortunately.
Okay.
But the material science is mind-blowingly cool. I hope one day we get to talk about it more.
Yeah, I like trying to figure out what the material is when people can't tell me what it is. It's my favorite hobby.
It's really crazy. Usually when you pick a material, we're like 3 digressions deep here. Usually when you pick a material, you want it to be as strong as possible so you can use as little of it as possible so you save weight. But the mirror only works when it's shiny. So to get the mirror shiny, like these wrinkles have like depth to them. So the way you get the mirror shiny is you stretch it, and I'm gonna probably tear it when I do this because I haven't edge conditioned this sample. But when you tension it, all of a sudden it gets specular. And so the amount that you have to stretch it is determined by the height of the wrinkles. And so the stretchier the plastic is, the less stress, less force you have to put into the mirror per unit area to get it to flatten out. And that stress is what sets the strength of the deployable structures in our spacecraft. So it actually counterintuitively means the weaker the mirror is, the lighter the satellite is, which is just mind-blowing. So cool.
One of the things I'm most curious about, honestly, is my experience of light pollution really is just I'm on the outskirts of Austin and I can look over towards Austin and I can see the light up in the clouds. So surely if you have any moisture or dust in the atmosphere, all we're going to see is huge spotlights coming down from space. Like, how are you approaching that problem?
This is a great question. This is, I think, one of the really hard ones for us to talk about responsibly, because, you know, Reflect is aiming to be the good guys, right? Like, I don't say that like I'm twirling my mustache way. I just mean, like, if this technology turns out to be bad for the world, we don't want to build it. You know, you can find us all over the internet. We've been accused of being frauds or, you know, attempting to end night, and, you know, we don't want to do any of that. We want to make the world a better place where clean power is cheaper and more accessible, because energy is really a tool of abundance. When energy has gotten cheaper and more accessible, lives have gotten better for everyone. And so we don't want to make life worse, is the long and short of that. So what does that mean for light pollution? Well, it means a couple of things. First off, it's a problem we have to study. We just in August presented a couple of papers at the SmallSat conference in Salt Lake City, Utah, about the effects of optical depth and light column visibility. The research was performed by Dr. Erwin Siddick. He's a longtime employee of the Jet Propulsion Lab. He has a doctorate, he does research in optics modeling, and so we're really trying to understand what factors and how we design and operate the satellite impact light pollution. And then another factor is like you said, where do we serve these spots? So it's very important to reflect that we serve these spots consensually over the entire spot area. So by keeping them concentrated, by keeping them near specular, we reduce the size of the area we need permission to avoid, you know, impacting others. But then also, you know, that's in our economic interest, right? Because the shinier the mirror is, the more photons we can sell. So it's always nice, I think, when the commercial incentives and the good behavior moral incentives are aligned, because that makes sure they're followed. And then also, as we track onto and off of our targets, we have to be responsible with where the spot goes. There are some ecosystems that are more sensitive to light pollution. You know, if you track over a city, you won't even notice. Each individual satellite is about, you know, a couple times the brightness of a full moon. So, you know, you really need to add multiple satellites together to get brightnesses that are effective to run solar farms. So you won't look up in the sky, you aren't at any risk of being blinded like you are with the sun. It's going to be a wild thing to see. It's going to be a very distributed light. And then as each individual satellite cycles on and off, we'll try and follow a ground track that disturbs the least disturbing ground track. But light pollution is a real problem. This is not a technology where I can sit here and promise zero light pollution. And I'm an amateur astronomer, right? I own a telescope, a very nice telescope that I love to take out to Joshua Tree National Park, and I love to do astrophotography with. I run star parties where I'll show kids the night sky. So it's definitely something where I feel a lot of responsibility to make sure that we help the world deal with the challenges of climate change, but also we don't leave behind a world that doesn't inspire the next generation to love space the way I got the opportunity to. Wow, that's very noisy. Hopefully that's removable from the audio.
It wasn't. So, Reflect Orbital have plenty left to prove. But among all the solar power satellite concepts, this one should be the easiest and fastest to implement. And if successful in this format, 12,500 of these satellites in orbit could give solar farms another hour of sunlight after the sun has gone down. At that point, it's a question of whether all that light pollution will be worth the cost. Ultimately, the cost of electricity is their limiting factor, but they also have plans to sell sunlight to big sporting events and other applications where huge floodlights aren't an option for some reason. Ultimately, I think space-based solar power is an eventuality if launch costs continue to drop. The question is, what form will it take?